Dynamic Monitoring of a Tennis Forehand for Training by Olivia Luke, Immy, Kniss, Rao, and Isabella Hasaj, a subteam within the HSTEM enterprise with a focus on combining the development of wearable technology and the growing demand for data-driven training methods in sports. Across various sports, training programs strive for two outcomes: injury prevention and performance optimization. Specifically in racket sports like tennis, chronic and acute injuries can arise, especially in child and adolescent-aged athletes who begin their athletic career young. One common injury amongst players is tendinitis at the shoulder, elbow, or wrist due to overuse or incorrect form. In conjunction with preventing these injuries, quantifying performance to improve and optimize tennis techniques is an attractive solution for coaches. With this in mind, we contacted the MTU tennis coaches to gather some input. We started with asking what the most important shot to focus on would be, which was the tennis forehand because it's utilized the most in all racket sports. We also asked what metrics they'd find useful. They said acceleration of the arm, joint angles, elbow movement in relation to the midline, and vibrations at the elbow. Lastly, they said the importance of the metrics would help them understand and adjust elbow positioning, timing of shots, and aid in identifying areas of stress in the arm to better performance and prevent injury. With the coach's input, we formed our problem statement, which is to develop a training device and technological platform to improve skill development and correct the form of a tennis forehand groundstroke for developing players. Our current design idea to approach this problem comprises of a compressive sleeve with integrated sensors at the wrist and elbow joints, as well as an attached sensor to the end of the racket. The wearable device would be paired with an app that would store the data and create a custom baseline for each player within an ideal range. The app would display relevant and understandable metrics as well as a visual rendering of the arm movement. The design would guide coaching corrections, optimize form, and prevent injury. The team's initial prototype consists of a breadboard configuration of an absolute orientation sensor and ESP32 microcontroller. The sensor is a 9-degree of freedom sensor combining an accelerometer, gyroscope, and magnetometer. The ESP32 was chosen for its Wi-Fi and Bluetooth capabilities for programming and processing. Although very early in development, the team has began testing the sensor by gathering position and speed data and looking into finding ways to effectively visualize the numerical data. Our future work in the upcoming semesters will include a focus on sensor initialization and calibration, PCB customization to miniaturize and optimize the design, and sleeve design and sensor integration. Our team would like to thank the listed departments and colleges and give a special thank you to Dr. Rao, our advisor, and the MTU tennis coaches, Kristen and Jamie D'Agostini, for their input, guidance, and support of this project. Thank you for listening.